Hi, everyone. My name is Brandon Rodriguez. Thank you so much for joining us today. This is our middle school student session looking at your questions and answers for the preparation of entry, descent, and landing of the Perseverance rover. The Perseverance rover will arrive on Mars in just a couple days now. And in anticipation of that, we wanted at the education department at JPL to address some of the questions you guys have. And thank you all for participating in the weeks of student challenge that we've been so privileged to be part of as you guys explore what it takes to get to Mars. I'm joined today by Elio Murillo, who is an engineer at JPL, who's going to talk us through a little bit about some of your questions. But before we get to those, I thought I could kind of walk us through what we've done to this point. So on our first slide, you'll see perhaps a website you're familiar with, our Mission to Mars Student Challenge website. This is a great resource to kind of take a look at how different phases of sending a rover to Mars takes place. You can see it's broken down across several weeks and broken down by grade level so that you can explore no matter what age you are. We really like this website because it's full of lessons written for educators and for students where you can kind of explore from start to finish the process that we go through. If you haven't been participating up to this point, please don't worry. Get started anytime. It's never too late. And you'll see that every week there's a little something fun to do. We have live streams such as this one all week, as well as guest spots from other great subject matter experts in JPL. On the second slide, you'll see my amazing colleague, Lyle, shown here, modeling perfect beard maintenance. And he leads several weekly videos kind of setting the stage for each of those challenges. So every week, as you decide what kind of part of the process you want to be taking part in, you can kind of get a little bit of a hint from him and our experts at JPL. On the third slide, you'll see just all of the incredible work that's been coming in so far. So we have a student showcase, and you guys have submitted hundreds of artifacts from your exploration of how one gets to Mars. And this begins with kind of planning our mission out, launching rockets, designing our spacecraft, right? We don't just fly off into space. We first sit down and we build our ideas. We build a plan and a strategy. And then on the fourth slide, you can see how it is that we've landed safely. So now that we've flown through space, how is it that you students have designed a safe landing technology? How are you going to do surface operations? Or how are you even thinking about how you're going to get samples back home in some sort of Mars sample return program? On the last slide, you'll see that this is, again, up year-round. So please participate and take a look at all the great lessons that are available for all K-12 students, whether you're at home or in the classroom. Just a really fun way to engage with us, to be part of the kind of scientific process that we're all so excited about. So with that being said, I wanted to kind of talk us through a little bit about what has gone before and what we're anticipating for EDL. So if you can imagine, at this point, we have traveled for over 7 months, for hundreds of thousands of miles, and we are now just 2 days away from reaching the Martian atmosphere. The Perseverance rover is encapsulated in between this back shell and heat shield, which, as it moves through the atmosphere, generates a lot of heat and friction. So the Martian atmosphere is thin, but yet thick enough to pose a little bit of a problem on that first movement into the Martian atmosphere. Now, that being said, when we are now moving tens of thousands of miles per hour, so how are we going to slow down? That first stage is via a parachute, and this provides some drag to kind of slow us down, but is not nearly enough to get us safely to the surface below. So instead, what we do is we use the sky crane technique, similar to what was used on the Curiosity rover, where the heat shield drops off, and then we literally drop the rover from inside. While an absolutely crazy idea, the retro rockets on the sky crane allow us to slow down safely and kind of scan the terrain. So at this point, we're coming to a much slower stop. We're scouting the area for a safe place to land that's not covered in rocks or a ledge. And then the sky crane will lower the rover down via a series of tethers and kind of drop it ever so gently just on the Martian surface. Once it feels the terrain underneath, the cords cut, and the sky crane flies off into the distance where it is safely distanced away from our Perseverance rover. At this point, the rover is now ready to begin surface operations. The mast will come up, and we will start communicating with it and explore Jezero Crater, looking for signs of ancient life. Really, really exciting stuff. And I think what I'm really excited to do is talk to our expert here about some of the questions and what we can anticipate for this EDL and surface operations. So with that, let me turn it over to Elio, who's actually going to take this first question, a video submitted question from a student. So if we could see that real quick.
Hi, my name is Isabella Garibay, and my question for the scientists in landing is there any water on Mars? And if so, does the water look or taste like water on Earth?
Go ahead, Elio, if you want to answer that question.
Great. Thank you guys for having me. I'm really excited to share a lot of what I know from Mars and, of course, the Perseverance rover. And that question, I think, is really important. Is there water on Mars? Is it anything similar to what we have here on Earth? Is there water? Yes, there is actually surprisingly a lot of water on Mars. It's a bit different, though, than how we would feel it here on Earth. Most of it is frozen. Something to be mindful of about Mars is that it's a very cold planet for the most part. And for there to be any kind of liquid water, it would have to be a warmer planet, or it would have to be the water would have to be very salty. Like you guys probably maybe right now in the Midwest, you guys are familiar with dropping salt on your sidewalks, and of course in the Northeast as well, so that melts the ice and actually liquefies the water. Similar concept. For there to be liquid water on Mars, it would have to be very salty, and we have witnessed some of that, but we know for a fact there is ice water throughout the planet. It's very visible on the north pole of the planet. So if you guys see pictures of Mars, you can see that there's this white cap on the northern pole. And then throughout the planet, there are many places where there's a lot of frozen water on underground or at the subsurface. So just maybe a few feet from the surface. And we're actually trying to go confirm a lot of that with some of the instruments on Perseverance, and we can talk about it as we go.
Yeah, awesome. Thanks for answering that. I think that opens up, obviously, a slew of great submitted questions online. The first one is, what are the main benefits of this mission? What are we really hoping to accomplish?
Yeah, so we're going after a few things. Obviously, one of the more exciting aspects of the mission, I mean, I think the whole thing is exciting, but one of the primary objectives of the mission is to go and look for evidence of biosignatures, evidence of life, either present or past. Was there any kind of microbe that lived on Mars in a certain past? The cool thing about Jezero Crater, if you guys have seen pictures of Jezero Crater, is that it looks very much like what the Mississippi Delta looks like today. So it's very clear that at some point in the past, water flowed through that area on Jezero Crater. And we know here on Earth, where there's water, there's life. So basically, we're trying to go find locations where over millions and billions of years, different materials could have been deposited because of that flow of water and could have preserved whatever was potentially alive there at some point in time. So we're going to go there and try to look at the geology, continue that study of the compositions of all the rocks and the soil on Mars, and also try and find if there's any kind of evidence that looks like organic material as a result of metabolic processes from microbes that could have existed at some point in time. So those are some of the very important aspects of the mission. Alongside that, there's a crucial aspect, I think, for human exploration in the future. There's a really cool instrument called MOXIE. something interesting about Mars is that Mars's atmosphere, first of all, it's very thin. It's very thin compared to Earth. So if you and I were to stand on the surface of Mars, our lungs wouldn't be able to breathe there because it's so thin compared to Earth. And our lungs are so specifically tuned to work on the Earth atmosphere. But one of the things on Mars is that the primary ingredient of the Martian atmosphere is carbon dioxide. And what we would have to know long term, if we're going to be, ever to have astronauts on the surface of Mars, how can we actually have that carbon dioxide? How do we convert it to something useful? And us, obviously, we need oxygen to breathe. So Moxie on Perseverance is going to take that carbon dioxide and convert it into oxygen on the rover. This is something we're going to have to master. It's a critical piece of technology. We would have to bring along astronauts in the future in order not only just to breathe, but also to create fuel for those rockets that would be needed to return home eventually, right? So many aspects of that are super exciting. And those are just some of the cool things that Perseverance will be doing over the next few years.
Yeah, I'm really glad you brought up Moxie. I know a lot of students are asking about, what is the survivability on Mars when we think about this, the harsh conditions. And I know that Moxie is just a pilot unit. So, this is really just a proof of concept at this point. So it's exciting to think that if this works, then we could perhaps scale this up and, perhaps have enough oxygen for people to breathe or to send samples back. So I know a lot of students are really excited about that potential. Looking at some of the basics, maybe you could tell us just a little bit about the rover. I mean, how is it different from Curiosity? Is it bigger, smaller? And what is our plan? How long are we hoping to be there and operational?
Great question. In many ways, Perseverance is very similar to Curiosity. It has a similar power source. It works on batteries that are charged by that power source. It has those 6 wheels, the rocker bogie mechanism. But in many other ways, Perseverance is way more efficient and more optimized than a Curiosity could ever be because of the updates to the computers that we're bringing along. Not only that, but our payloads, all of our instruments are more capable, and the cameras too. The cameras on Perseverance are going to let us see Mars like we've never seen it before. We're going to get way crispier images. Everybody's going to be able to take a look at what comes from Mars, and more information on that is going to come out over the following weeks on how to access that. And it's really exciting because we're really going to, Perseverance at the end of the day is an extension of ourselves, right? We can't bring ourselves quite yet to Mars, but Perseverance is bringing those eyes and ears, because also another really cool thing about Perseverance is that it's going to have a pair of microphones. So we're going to be recording a lot of the sounds, not only on the surface, but also that entry, descent, and landing. So we're going to be hearing for the first time what that's like, and having, experiencing that in a way here on Earth, which is really, really cool.
Yeah, it's funny to think about the rover having like the senses for us, right? In one of our previous sessions, we talked about getting whiffs of methane, right? Like, our rovers have noses and ears and eyes, and that's how we are able to actually get the data back to us. There are actually a couple questions from some students wondering just about that data. So as we perform surface operations and we explore the surface of Mars, what does NASA do with this data? What does it look like, and how does it reach the community, right? And it's obviously more than us that is excited about this. Could you maybe comment a little bit about what happens next? What do we do with this data, and how do we kind of move forward scientifically?
That's right. So a lot of that data will be collected, every single soul on Mars, and transmitted over periods of time. Something to be conscious of with Mars is that we're not connected to the rover, every single hour of a Martian soul. So we have to be very conscious of and very smart about what data do we consider important enough? How do we package it so that we can transmit that back to Earth in reasonable amounts and reasonable bandwidth? internet is really fast. So, everybody's really used to instantaneous transmission of information here on Earth. Can't quite do that yet on Mars, or with the assets we have on Mars. But we do get reasonable, gigabytes worth of data over time that will allow us to transmit images, scientific data, and all of this eventually goes to the public, right? We do have the science teams that are, assigned to specific instruments and are expecting data to come from these specific instruments. And eventually a lot of this data becomes public, so that the citizens and universities around the world can also take this data and run their analysis. That way, many people have their eyes on the data and more conclusions can be made of the data. And it's really exciting because it's this is all, publicly funded. So all the data we collect does eventually become public.
Yeah, you mentioned, how it is that we get this data, and obviously with the vast distance in between us and Mars, that we can't just get this data in a blink of an eye. But could you comment a little bit? What does the process of sending and receiving data look like? I mean, we're not even speaking directly to the rover on Mars. We kind of speak through an intermediate. Could you kind of detail that for us?
Yeah, it actually depends. We do have ways of speaking directly to the rover, but most of the time we're using our orbiters. So we have these satellites orbiting Mars that have connections with our arrays here on Earth called the Deep Space Network. And I invite everybody to look up what that is, because we have these massive antennas, the size of like the Disney Cinderella castle. They're really large, and we have one here in California, one in Spain, one in Australia. And as you can imagine, if you place those different antennas across the planet, as the planet is spinning, we have, almost full visibility into everything around the solar system. That allows us to have connection with Mars as long as Mars is within our line of sight. Because there are parts during the year where Mars is going to hide behind the sun. So we can't quite penetrate through the sun to talk to Mars. So there are periods of time where we can't communicate with the rover. So it's crucial for the rover to be able to survive on its own during those periods of time. Now, the way we talk with the rover on a daily basis is, as you can imagine, these different satellites, going around the planet, we can time exactly when what satellite is talking to one of the rovers. That way we can actually command the rover, as well as tell the rover, hey, I want this amount of data today. Give me this amount of data during this particular time. And then we receive that on Earth, X amount of time later. Mars is far enough where, depending where Mars is on orbit, a signal can take, between 6 to 20 minutes one way. It just kind of depends where we are across the solar system. And that's about how far Mars can get. So imagine, commanding something. It doesn't actually take, it's not immediate. It'll take about 6 minutes for that command to get to the rover. And same thing, whatever we're trying to get from the rover on Mars, it takes about 6 minutes to travel back through space. So it's pretty far out because it's going at the speed of light. But our solar system is pretty big after all.
Yeah, I think I told students one time in the past that the way we interact with the rover is similar to when your parents tell you to do some chores. So they're not saying, hey, I want this bed made and this, the kitchen cleaned at this time. They're saying, by the next time I'm here, that's when I want it done. So, I think if I understand correctly, the rover does have some autonomy as well, right? We send it quite a bit of directions, but it does have the ability to kind of choose a path sometimes, and it can make decisions in its best interest, if you will. Is that the case? Is that an okay assessment?
That is a fantastic analogy, where yes, there is some truth to that, where we tell the rover, hey, I want you to move X amount of distance. I want you to go from point A to B. But one of the benefits of Perseverance in particular is that it has increased autonomy. So it can actually take images, take decisions as to what path it wants to take to get to that point we command it to. So if we run into a rock, the rover's not going to drive into that rock. It's going to make decisions, so it actually drives around and gets to that point where we've commanded it. So the rover does have that intelligence to be able to make those decisions and not mess itself up by running into a rock or climbing over something that's too steep, or dropping, or it detects edges. It won't just drive itself into a canyon, for example. It has plenty of limitations, and our cameras and our computers let it make those decisions very intelligently. And a lot of that is we have a lot of confidence in because we test it here on Earth. And that's actually what I do for day to day. A lot of these sequences and a lot of these commands and these autonomous behaviors, I go and test in the Mars yard. We have this area at JPL we call the Mars yard, which is just a bunch of sand, a bunch of rocks and pebbles, and we have Earth's sister of Perseverance. Optimism is the Earth version of the rover that we command, and we send these sequences and we test all these things so that we have full confidence that before Perseverance does it on Mars, these commands actually work. So this is why we now have the confidence to say, yeah, Perseverance is going to do its thing successfully on Mars, and it's going to listen to us because it knows what to do, because we're testing it with the sister Optimism here on Earth.
Yeah, it's really cool. I think seeing the Mars yard is one of the favorites for any visitor of JPL, right? Being able to see this simulated Martian terrain, and to see you guys driving out this engineering model of the rover. I think I recall hearing too that one of the other advancements over Curiosity was during EDL that there's some increased ability to kind of select a landing site as well. Do you know much about that? Could you comment on that?
I know a little bit about it. I don't know the exact technical details, but the big difference, I think, is that there are additional capabilities. Again, it comes down to that same computer that we've added to make the rover be able to drive more autonomously. That same computer during EDL, what it does is that it takes images real time and process them and creates a map of what it's seeing. That way it can actually process and detect obstacles so that the descent stage, that jetpack that you guys may have seen in the 7 minutes of terror video, can actually deviate to flatter conditions. That is why we are now landing in a more precise location. And Jezero Crater, compared to Gale Crater, where Curiosity landed, has way many, it's way more complex. There's many more rocks. There's more features that could potentially be dangerous. But because of this level of autonomy, of taking images as we're landing, the vehicle can take decisions to land in the flatter, safer terrain so that it can, guarantee a soft touchdown. It's really exciting, and it's really one of the big advancements with the mission, because many companies later on are going to be relying on this data to improve their algorithms as well. So one of the cool things about this is that it's we're using it to advance the commercial side of things, and even feeding into the Artemis mission to the moon in the upcoming years. So there's a lot of excitement behind this particular piece of this aspect of the mission of landing, and it's called relative terrain navigation. That's going to be used all over, and we're really excited about it.
Yeah, that's a really great point. I kind of I wasn't really thinking about it that way. Just how much of this is in itself setting the stage for the next steps, right? I mean, we talked about Moxie as kind of a proof of concept, but it's only one of many advancements, and how we learn from those will shape what the next missions look like. It's kind of exciting. Like, the process never ends, right? I guess you generate more questions than answers every time.
You do, and a lot of these technologies, again, we're going to reuse them on Mars, but we're also going to be learning so that those humans that are going to the moon in upcoming years can also, land safely on the moon. That this all feeds into the greater NASA picture, and it's fascinating how everybody contributes, and these small little pieces of technology that some people may be working on have a lot of impact in the future of the space program. So it's very exciting.
Yeah, speaking of those advancements, some students are wondering, another big change from Curiosity is this idea of rock coring instead of rock drilling. Do you know much about this? Could you comment on kind of why this is exciting and why we would want cores versus looking at powder analysis?
Yes. one of the critical aspects out of the many, because I've spoken about a few already, is that Perseverance and the Mars 2020 mission is part of the greater Mars sample return campaign. So something to be conscious of is that we've never actually returned anything from Mars. We've only ever sent landers, we've sent rovers and orbiters, which are obviously very important and very difficult things to accomplish. But Perseverance, not only is it going to be able to drill into rocks and look at samples on the spot, the teams here on Earth are going to decide, hey, this rock over here looks very interesting. And we have, there's only so much we can do with the instruments on Perseverance. You know what? Let's take this rock and core it and package it in a tube so that then a future mission can go pick up that tube and bring him back to Earth. That is something obviously that we're very excited about because we've never done anything like it from Mars. The rover is fully capable, and it has the most complex robotic system we've ever flown in space to do that. The arm itself is going to be able to core, is going to be able to point itself at some rock that we tell it to, core some rock that we find interesting enough, take it from the rock, bring it in, and almost you could think of it like it's eating a rock and storing it inside of the vehicle and eventually drops it off somewhere. And then some other mission in the future is going to go pick it up. So it's very important that we do this successfully. And we're going to collect something upwards of 30-something samples to eventually return to Earth. So very, very exciting, something we've never done.
Yeah, I absolutely share your excitement for this. I think that it's really interesting. There's a lot of narrative and a lot of student questions and excitement about sending people. But in a very JPL fashion, I've always said, don't send people to do a robot's job. They seem to be doing really well. They don't need food. They don't need air. They don't complain if we, don't talk to them for a day. It seems like bringing Mars to us, where we have, granted, Perseverance is the most advanced rover, but as you said, nothing will ever be the same as being able to study with all of the resources here at home. So Mars sample return makes sense to me. I want to be able to look at these samples and then go home at the end of the day, not be stuck on Mars with these rocks wondering, did I find life or not?
That's right. And there are many aspects of sending humans to Mars that's really challenging. And like you mentioned, yeah, a robot is hungry in a different way than humans are. A robot doesn't have to be awake for 7 months in a space capsule as it gets to Mars. Things to think about, because I can't imagine personally being in a space capsule for 7 months, then landing on another planet and then being stuck there for quite some time before being able to come home. That's, like you said, it sounds like a robot's job to me. But in the future, we'll see where the Martian architectures go. And obviously, we're preparing for human exploration eventually. It's something to look forward to in upcoming decades. And for all we know, one of those first Martian astronauts is watching this talk right now. And I hope that's the case.
Yeah, awesome. Maybe we could talk a little bit about some of these advancements. So while we are there and we have all this new suite of amazing instrumentation, what are you most excited about, and what do you think we will learn? I mean, obviously, if there were some sort of evidence of biosignatures, that's clearly groundbreaking. But realistically, looking at every instrument on board, what are you most excited about?
So something I haven't talked about yet, and I'm working on as well, and I'll be one of the pilots for, is the Martian helicopter, Ingenuity. Everything we've already spoken of is really exciting, and I think it's crazy how within a span of nearly 100 years, a little more than 100 years, where we just started flying airplanes and helicopters here on Earth, we're going to be flying a powered vehicle on another planet. That is something that's never been done. Ingenuity is the first of its kind helicopter that will fly on another planet and provide that new level of exploration, right? This aerial view, something we've never really done. We have our satellites on orbit, but now we have this, you could think of it almost like a scout potential for different types of missions in the future. Ingenuity is going to be what we call a tech demo. It's another proof of concept so that we can explore, how do we fly helicopters on Mars? We know we can do it. We have ways to test that here on Earth. But what are the implications? Mars is really cold. The atmosphere is very thin. So only so much energy can be used to generate enough push to, fly on the Martian atmosphere. And how many images can we take? Can it actually help us map the terrain to help Perseverance explore the surface? These are things we're going to be exploring. And then eventually, right, in the future, when astronauts get to Mars, they may have, many of these scouts accompany them. There's so many aspects of the Ingenuity mission that are really exciting as well, because they're just going to teach us how to explore Mars in a new way. So that's, I think, one of the parts I'm really looking forward to. And I'll actually be part of the team piloting Ingenuity. So I'm really excited about that in the coming months, and it's going to be awesome.
Yeah, that's pretty exciting. The plan is to begin surface operations with Perseverance, and then Ingenuity will have some test flights a little while after. Is that correct?
That's correct. So over the next few months, be on the lookout for announcements. For the first several weeks on Mars, we have to commission, make sure the rover's healthy, make sure the instruments are doing well, everything checks out as expected. And then we'll eventually start driving, and we're going to be looking for a spot where we can drop off Ingenuity and start flying it. That's going to be happening over the next few months. So be on the lookout, and it's really awesome. It's exciting.
Yeah, most definitely. I think, one of the theme I see here from the student questions I think is important to talk about too is not just the individual instruments, but the process. So we get a lot of questions about, how many people come together and work on this. What do teams look like? I mean, clearly, it's not just one person. So what does it look like to kind of design this and prepare for an event like EDL or surface operations?
This is an excellent question, and it takes a long time to go from idea to actually landing on Mars. Perseverance has the benefit that a lot of its architecture does stem from Curiosity and the previous Mars Science Laboratory mission that landed in 2012. So we've recycled some of it, but it's still, that was 2012. Perseverance started planning, sometime in the late, 2000s, like 2008, 2009, something along the lines. And it's taken, a little more than a decade to go from that to now getting to Mars. And through all that time, right, we have had thousands upon thousands of people, not just from JPL, but from universities across the world, different organizations helping us build particular pieces of hardware, not only from the United States, but also from Europe. And it's a partnership that's taken a lot of effort, many hours, worked by thousands of people. And I really do appreciate the name Perseverance, because even though, we've all been through this pandemic, we're all going through it together. We have had to adapt working from home, right? It didn't stop us from getting the rover to Mars. And I think it's testament to the effort of the team. And it's been an honor, right? It's been a privilege to be part of the team. And I'm always working with very intelligent people, learning from everyone. It's not easy, is what I will say. It is not an easy task to get a spacecraft to Mars, but many of us, obviously, this is what we thrive for. We're making sure that our we can go do science on another planet. We can go explore the universe and learn more about what it is that what sprouted life here on Earth versus potentially on other planets. All these questions are open, right? And this is what we're going after. So it's an awesome thing to be a part of.
Yeah, most definitely. I think it's really, really motivating for students to just hear a little bit about this. I think every session it's important to kind of talk a little bit about pathways to kind of, whether it's at NASA or not, but jobs in STEM that you love. And it seems that a lot of students ask, how can I work at NASA, as if there's just, one door you walk through and you're in. But, just as you mentioned, a lot of this instrument design and design of the rover takes place externally as well. It takes place internationally. We are the, kind of just the beacon of all at once together, but, partnership with universities and internships, and there are so many avenues to get here. Maybe you could talk a little bit about, your path. How did you get to NASA and JPL?
Yeah, it's crazy because about 10 years ago, I was exactly where many of these students may have been, maybe a little bit older. 10 years ago, I was just, middle of my senior year in high school. And now 10 years later, here I am after going through, university, went to grad school. Here I am at JPL, working on an incredible mission that's going to go explore another planet. This is literally a dream come true, something I've been dreaming of since I was a small kid. I grew up in Puerto Rico, where I am the first engineer in my family. My mom was a teacher, so something that was always very important at home was, school is important. We have to do very well. School was my way out from poverty. That's what it was. I grew up in a low-income household, single mother household, where she just always worked and made a ton of sacrifices to make sure I was doing well. And I managed, even though that's the background I come from. I went to University of Michigan, where I did my undergrad in mechanical engineering and electrical engineering as my minor, and then went off to grad school and did spacecraft design. So these are, possible routes. You don't have to have all the money in the world to do it. There are scholarships. Even if you have to take out some loans, it's okay to do that, especially in STEM fields where, we earn good amount of money. It's the reality of it. And I will forever be grateful for, all my teachers that have invested all their times to, be in events like this one, where we would get to chat with engineers and people we could look up to, so that we know it's possible to get here. It's not like I've done this all on my own. I've had plenty of mentorship, incredible teachers, incredible friends that support each other. And that's, in a gist, what got me to where I am today. It requires discipline. Being an engineer is not easy. Even now, school is not easy for engineers, but it's worth it. There's so much you learn about yourself. You have to use all these creative tools you've developed over the years. Even if you think you don't like math, maybe engineering is for you. I'll speak for myself. I'm not the craziest fan of mathematics. I can't just multiply things off the top of my head. I don't do that. I write code that does that for me. It's just the way things happen. And I love building things, right? I love building things, figuring out what broke them, debugging things. These are things I have to do day to day at my job now, and I get paid for it. It's crazy, where I have to go figure out why something broke, debug it, test things, come up with solutions, and work with other people, right? It's not like I have to know everything in the world. I work with an incredible set of people that I know I can go rely on and say, hey, I don't actually know this. Can you teach me about it? Can we talk about it? Can you kind of show me these drawings? Like, what does this mean? Why is this happening? You don't have to know everything. It's a learning process. It's always a learning process. We're learning things every day. I can't tell you that anyone else is working on a Mars rover in the world, because no one else is, right? A lot of these problems where we run into day to day, it's the first time anyone's ever run into them, right? Maybe we have some experience from Curiosity and previous rovers, but at the end of the day, this is a new system. This is a new piece of technology, and we have to figure out why things are happening, debug on the spot, come up with solutions, because eventually all these implications will affect the rover on Mars. So it's exciting. It keeps me busy, keeps me motivated. And, I'm happy to share all these experiences, because I always like to tell people this is possible. I'm a testament for hard work, and sticking to my dreams as I always have. And, sacrifices are required, but here we are, right? About to land on Mars, and it's really exciting to be a part of this.
Yeah, you covered a lot of really important points. The one I'm trying not to fixate on is the fact that 10 years ago you were in high school. So I'm very much an old man in comparison. But certainly when it comes to exposure for students of color, I think it's really great that you take the time to kind of share with the community and show them that they too can be scientists. I think that's the biggest problem facing young kids of color, is that they don't know they can be a scientist, right? And that's where it has to begin. And kind of in a similar vein, you mentioned that you get to this job, the dream gig, not because you know everything, but because you're driven, right? And that's another thing I really want kids to hold on to, is that we don't get here finished products, right? We don't know all the answers. In fact, we learn every day. I'm intimidated almost every day being at JPL and be surrounded by such great minds. But that's the fun part, right? That's the most exciting component, is knowing that we continue to grow and the job is, new and exciting every single day. So I'm really, really happy that you highlighted that.
Yeah, I think it's important because it's not like we have answers to everything all the time. We struggle. We're banging our heads on the keyboard trying to figure out why something isn't working. We don't always have the answers. And sometimes we do have to actually take a step back and say, hey, we simply don't know, but here's a workaround for this problem. Here's how we can actually still move forward. And it's a testament to perseverance, right? Like the name, again, it can't be more perfect for the rover. We just keep pushing through because that's what we have to do to get this rover to be, safely on the ground and to meet its mission.
Awesome. Well, I want to thank you so much for taking the time to answer these questions and speak to our students. Really, really appreciate it. I hope that everyone watching will tune in Thursday at 11:15 for the pre-landing show, and then shortly after noon Pacific time is when we can expect EDL to take place. So lots to be excited about. Get out there, keep doing all these awesome things in science, participate in the Mission to Mars Student Challenge, and thank you guys so much for joining us. So have a great one, and looking forward to seeing you on Thursday.
Thank you guys for having me. And also just a quick shout out to the NASA en Español event that's happening. There's going to be an entire program in Spanish. Tell your parents, tell your grandmas, your grandpas to go look at this if it's relevant to you, and hopefully they get to enjoy this along with you.
Hi everyone, I'm Emily. NASA is landing the next rover on Mars in February, and they want kids from all over the world to join in the excitement. They're inviting educators and families to lead students in designing and building their own mission to Mars. Then, land with perseverance on February 18th. It's the Mission to Mars Student Challenge. With 5 weeks of activities, professional development for teachers, and opportunities to chat with engineers and scientists, NASA's Mission to Mars Student Challenge has everything you need to bring students from brainstorming to liftoff all the way to Mars. Register your students today to join NASA as they prepare to touch down on Mars, and I'll see you on landing day. Touchdown confirmed, we're safe on Mars.
How often do you get to say you work next to a robotic system that's going to Mars, right? There's not many places in the world that you can do this. My name is Eric Aguilar, and I'm working on a robotic system that will be collecting Martian rock samples so they can be studied on Earth. This is our Hexapod Testbed. It's basically a rover body that allows us to attach, a robotic arm, the adaptive caching assembly, the drill. So that's where a lot of the testing happens behind me. The sample caching system will use a robotic arm and drill to actually take samples out of the ground. And we're looking for evidence of life that may have existed on Mars. The smaller arm that lives inside the belly of the rover and is used to actually process the tubes as they come back with a sample inside. We'll measure it, take some pictures of it, and get it sealed and stored for a future mission to pick them up. You see the robotic arm stretched out, and we have a bunch of engineers and technicians working on installing a model of our drill. Working in aerospace, that was always a passion of mine. What really draws me towards it is the engineering of it. Always working on something new and something that's never been done before. Finding those problems, getting them fixed is really something that I enjoy. In 20 years, the children will be reading this in their science book and kind of cherish that.